Hi everyone, my name is Eric. I currently work as an electrical instrumentation and controls engineer based in Chicago, and I have a bachelor's in electrical engineering. Today's topic we'll be going over is Laplace transforms, what purpose do they serve, and we'll be kind of going over a couple of questions, solving them. So let's get started. So one of the first main reasons we do Laplace transforms is that when you're taking your differential equation classes, it's usually you're given very complex situations and very complex numbers. And essentially what we're doing is we're taking problems and converting them from the time domain and converting them to the S domain. And essentially what we're doing is we're taking these complex numbers and converting them to algebraic expressions. So I have a couple of problems we're gonna get through today, and we're gonna go one by one, and we're gonna kind of go from like easiest difficulty to later on pretty difficult problems. So let's get started. I do want to mention that Laplace transforms you're typically given kind of like a table or a rubric, but it's also good to kind of have these memorized so you don't have to kind of find these online, or if you're also studying for the FE exam through the FE reference handbook. But regardless, so one of the easiest and most basic kind of Laplace transforms you'll see in the time domain is phi of ut. And essentially, whenever you're given the functionality of u of t, the conversion of that to Laplace, when you're utilizing this and converting it through Laplace transform, it's actually converted to 1 over s. So in this case, our coefficient in this case is 5. So all we do is we put the 5 in the numerator and then the s is in the denominator, and that's our solution for this problem. Okay. The next one is a little bit different. It's a little bit trickier. But whenever you're given a functionality like this, my recommendation is taking the 6 out for the time being. So we're going to have 6 over here for now. And then we can say multiplied by e to the negative 3t. And when you take the Laplace transform and you take this from the time domain, the S domain for these kinds of functions of e to the negative t look like 1 over s plus the unknown, which in this case we'll just call a, and that's it. So that's what it should be configured to. And actually, one mistake I made is actually your a value is represented in the coefficient in the exponential. So that's actually what you do. You take this and you convert it to Laplace transform, you get this. So in this case, what we have is because our 3 is negative, in the denominator is going to stay positive down here. So actually it'd be 1 over s plus 3. And the only thing we have left is to bring back this 6. And so we multiply this by 6. So then we get 6 over s plus 3. And that's that for this one. Oops, this should be plus. Here we go. Pretty straightforward. And then this is a third kind of functionality. If we were to take the time domain expression of this, it should look like this. So it should typically represent it like this. And so what's different here is that if you look at the exponential in this case, it's positive. So when we get to here, it'll be a little bit different. But when you get the t function as the coefficient in this case, what we're going to do is the Laplace transform to this is actually going to look like this. 1 over s plus the unknown in this case, and then we square it. So that's what happens in this case. So in this case, the denominator is going to be squared. And so to take this example where the 2 is positive, we're going to, and the coefficient, there's no values. There's no like 3 or 5 over here, so we don't have to worry about that. The t is expressed in the denominator as an exponential. So what we do is to convert it from the t domain to s domain, it would actually be 1 over s minus 2 squared. And that's what we get for this. Awesome. I'm going to erase the board. We're going to do a couple more problems and go from there. Okay, so I have 2 different problems. These are going to be a little bit trickier, but we'll kind of walk through it together. So in this case, we have 5e to the power of negative t times sine to the 5t. In this case, the Laplace transformation for this, so from the time domain, what it would look like is one of the formulas that you can look up online is e to the negative at times sine beta t. So that's what we have here. And to convert this to the s domain, what that actually looks like is we have b at the numerator, and then we have s plus a unknown squared plus b squared. So that's what we have. So if we were to break this down, essentially, if I took this formula and I put it down here, so then we can visually see what's going on. Negative t times sine, and our b is 5t. That's what it would look like, right? So our variables are a, unknown, is negative 1, and, or apologize, it's 1, right? And our beta in this case is 5. So all we do is just plug it into this formula, right? So beta we got is 5 over s plus a, which in this case is the negative function of this, which is just we keep it. So it'd be s plus 1 squared plus beta squared, which is 5, which is 25. And the only thing we have left is, if you remember, we want to not forget this coefficient over here, which is 5. So we multiply this whole thing by 5. And so our solution for this problem would actually be 25 over s plus 1 squared plus 25. So that's our conversion from the time domain to the s domain for this function. And then for this one, if I were to give you the formula for the Laplace transform for this, it's very, very similar, but it's still going to be different. So it would be negative e to the negative t times cosine beta t. But when we convert this and do the Laplace transform of this, what we end up getting is we get s plus a in the numerator over s plus a squared plus beta squared. And so what's also trickier about this is that we don't actually see this anywhere, right? We don't see the e to the power of negative t function anywhere, right? And so what we have to actually realize is that when you do e to the negative 0, so t would actually be 0 in this case, this becomes 1, because this is 1 over here, right? Because we don't see this represented, so that means that the a unknown is actually 0. And so if we plug in 0 to here, we get s plus 0 over s plus 0 squared plus our beta, which is also technically not a visible value, but it is there, which is a 1 over here. So beta is actually 1. So then that means 1 squared is just 1. And the only thing we have left is what we did in the previous problem, is that we still want to carry that coefficient, so we multiply this whole thing by 6. So what we actually end up getting is 6s over 0 is here, but it's still going to be s squared plus 1. And that's our solution for this. Awesome. So if you guys have any questions, leave it in the comments. But otherwise, that's how you do the Laplace transforms for a lot of the ones you see in your differential equation classes, or maybe you're going to see it in control systems or linear systems or any of that good stuff. So very good and useful to know. So awesome. Enjoy.